Okay. So this is a team project with Julia Hylak, Maciej Domoracki, myself, and Krzysztof Tomala. The project leader is Pablo Ribalta from NVIDIA. And it's about NeRFs, neural radiance fields. So first, I'll start by explaining what those are. So the problem is we want to do a view synthesis. So we have a scene, and we want to have some kind of representation which will allow us to provide a view, give a position and direction for a camera and provide an image of that scene from that point of view. And the way we do that is by this paper on representing scenes as neural radiance fields for view synthesis from 2020. And the solution is we have some kind of function, f, which is for given positions and direction. We can make out a density and color at that point in space. And we have some kind of view. And for each pixel in that view, we cast a ray through the scene. And for each point on the ray, we figure out what the 3D density and color should be at that place. And after we have that, we get some kind of function, which is four-dimensional, I guess, with density and color. So 1 dimension for density and 3 dimensions for color. So yeah, in this case, we have a brown spike over here. And this is the only large density, so we color this pixel brown. And likewise, we have orange and yellow spikes here. So we color the pixel orange because it's before the yellow spike. So it's more closer to the camera. So yeah, in more detail, this is what the architecture looks like for the original NeRF. Yeah, we have some positional encoding. We have multiple layers, and we also encode direction. So this is for reflection, because from different points of view, the color might be different. And yeah. The definition for the color of the array is as follows. This is an integral with 3 parts. Starting from the right, we have the color itself. We want to average over that. But we also have the density at that point. This is also pretty straightforward. And there's the t. This t stands for the part which is proportional to the amount that this particular spot in space is not yet covered by previous pixels. So yeah, the definition is it's inversely proportional to the previous densities along that ray. And yeah, we calculate this integral by just approximating it. And yeah, also a word on the positional encodings I mentioned. Instead of just providing the positions themselves, we provide sines and cosines of it. Yeah, and these are just better features for representing 3D points. You can see the difference with or without the positional encoding. And yeah. For majority of the rays, or majority of the points along those rays, the density will be close to 0 because it's just air between the actual objects in the scene. So we want to sample the places where actually the density function is larger. So we want to oversample on those places where, yeah, there's more things. So first, we sample uniformly, as I said previously. but then based on the outcomes, so the densities, we sample again, and we take the union of those samples to calculate the color. Yeah, and this is the loss. We minimize it, and yeah. We train on a single scene. We come up with a trained model for representing only one scene. And yeah, these are some examples. On the left, two images. We have ground truth and NeRF, and also some previous methods on the right. As you can see, NeRF reaches very good results. Also some videos. So yeah, thing about NeRF is there are a lot of different flavors of them. So first we have the vanilla NeRF, but also, for instance, MIP NeRF is a flavor of NeRF which is used for creating faraway or downsampled images. The problem there is if we want to downsample the image, we don't want to do it naively, and we want to basically do anti-aliasing, and this is a good way to do that. Instead of considering rays, it considers cones there. So instant NGP touches the positional encodings I mentioned. Instead of using those, it replaces them with a few predefined features which are lower dimensional, so it makes it faster. NeRFacto is just not actually based on any paper. It's instead a combination of multiple different NeRF flavors. And yeah, on the right there's a bunch more. I will not go over all of them. Yeah, so the plan for our project was to first benchmark all of the models. So we decided to capture various quality metrics of the reproduced images, as well as train time and inference throughput. The second part of the project was to analyze the PyTorch profiles, to look at different PyTorch profiles, and then, based on those profiles, implement our own NeRF flavor. This was an optional part of the project, and unfortunately we didn't manage to complete it. But yeah, for benchmarks we trained in 4 different regimes with, depending on the number of GPUs, and different number formats. So we used single GPU versus 4 GPUs and fixed versus mixed precision. And we generated this scene. So yeah, we collected a bunch of numbers. So we have 3 different kinds of accuracy metrics. First one is, I guess you can think about it as a simple mean squared error between ground truth and synthesized image. Structural similarity, second one is more aligned towards comparing images. It looks more about where the pixels are, and LPIPS is based on a similarity between latent maps of feature maps from processing that image by some neural network. And yeah, it turns out that this is a good way to compare images. And as I said, there's also time to train and throughput measured. So yeah, from this, we realized that hash NeRF performs very well. And yeah, also, as I said, we have PyTorch profiles. So those are basically call trace of the Python functions, and on the horizontal we have time, and the idea was to take a look at those and look for places to optimize those long functions. We could potentially gain some information and have a starting point to optimize this. So yeah, that's it from my side. Thanks.